The question sounds informal, almost careless, yet it exposes one of the deepest problems in modern science. Where are the aliens? It is not a question born from imagination or fiction, but from mathematics, time, and observation. In a universe governed by physical laws that appear consistent wherever they are measured, the absence of visible intelligence is not a neutral outcome. It is data, and it demands explanation. The universe is ancient. Current measurements place its age at approximately 13.8 billion years. The Milky Way galaxy formed early in that history and has existed for more than 13 billion years. Our own solar system arrived very late by comparison. The Earth formed roughly 4.5 billion years ago, making human civilization an event confined to the final fraction of cosmic time. Long before the Earth cooled, before oceans formed, before life appeared here at all, stars were already forming planets throughout the galaxy. Entire stellar systems lived, evolved, and died before the sun ignited. Time alone creates a problem. If intelligence were even moderately common, it would not be young. The Milky Way contains between 100 billion and 400 billion stars. Over the last few decades, observations have overturned earlier assumptions about planetary rarity. Planets are not exceptions. They are a standard outcome of star formation. Most stars host planetary systems. Many host multiple planets. A significant fraction of those planets orbit at distances where liquid water could exist under the right conditions. Conservative estimates indicate that tens of billions of potentially habitable worlds may exist in our galaxy alone. This conclusion does not rely on speculation. It follows directly from observation. Life on Earth emerged relatively quickly once conditions stabilized. Geological evidence suggests that simple life appeared within the first billion years after formation. Complex multicellular life required far longer, but once it appeared, diversification accelerated. Intelligence capable of abstract reasoning and advanced tool use arose only once, yet its emergence demonstrates that such outcomes are not forbidden by physics. No known physical law prevents life from arising elsewhere. No unique chemical property confines biology to Earth. No cosmological constraint singles this planet out as the only location where consciousness can emerge. From this, a straightforward expectation follows. If even a small fraction of habitable planets develop life, and even a much smaller fraction of those develop intelligent species, then over billions of years, galaxy should host multiple technological civilizations. Some would be younger than humanity. Others would be vastly older. Many would have emerged millions or even billions of years before Earth existed. Time alone grants them an overwhelming advantage. Technological progress compounded over geological timescales becomes profound. A civilization does not require faster-than-light travel to spread through a galaxy. Sublight expansion, proceeding cautiously, sending probes or settlements between neighboring stars over thousands of years, would be sufficient to traverse the Milky Way in a few million years. On cosmic timescales, this is negligible. The galaxy is not vast when compared to the time available for exploration. If any civilization had arisen in the Milky Way even 10 million years before humanity, it would have had ample opportunity to leave detectable traces. Artificial structures, altered stellar energy usage, atmospheric changes on planets, waste heat visible in infrared surveys, persistent communication signals. None of these require extraordinary assumptions. They follow directly from known physics and engineering applied over long periods of time, yet none are observed. The sky is quiet. Radio surveys detect natural phenomena such as pulsars, quasars, stellar flares, and cosmic background radiation. but not persistent narrowband signals associated with deliberate transmission. Infrared observations do not reveal stars surrounded by large-scale energy-harvesting structures. Spectroscopic analysis of exoplanet atmospheres has not identified industrial pollutants that defy natural explanation. No confirmed probes, no verified artifacts, no unambiguous evidence of extraterrestrial technology. This discrepancy between expectation and observation is known as the Fermi Paradox. The name originates from a moment attributed to physicist Enrico Fermi during a lunchtime discussion in the middle of the 20th century. Confronted with the growing awareness of the universe's size and age, Fermi reportedly asked a simple question: where is everybody? The significance of the question lies not in its phrasing, but in its implication. If intelligent life should be common, its apparent absence requires explanation. The paradox does not assert that aliens must exist. It states that, given reasonable assumptions, their absence is unexpected. It forces a reconsideration of foundational premises. Perhaps intelligent life is extraordinarily rare. Perhaps technological civilizations do not persist long enough to be detected. Perhaps advanced intelligence behaves in ways humans do not anticipate. Perhaps evidence exists but remains unrecognized. Or perhaps something repeatedly prevents life from advancing beyond certain thresholds. Each possibility carries different implications for biology, intelligence, and long-term survival. The paradox does not rely on optimism, hope, or expectation of contact. It relies on multiplication. Stars multiplied by planets. Planets multiplied by time. Time multiplied by technological capability. The outcome should be abundance. The observation is emptiness. This emptiness is not merely philosophical. It has practical consequences for how humanity understands its place in the universe. If intelligence is common but short-lived, then survival becomes the central challenge of civilization. If intelligence is rare, then its preservation becomes uniquely significant. If advanced civilizations exist but remain silent, then caution may be rational. If no others exist at all, then consciousness may be among the rarest phenomena the universe has ever produced. The Fermi Paradox sits at the intersection of astronomy, biology, physics, and long-term thinking. It is not a question about visitors or sightings. It is a question about probability, longevity, and the behavior of intelligence under physical law. And it leads directly to a problem that cannot be avoided. When the numerical foundations of this silence are examined carefully, without exaggeration or speculation, the absence of visible civilization becomes even more difficult to dismiss as coincidence. To understand why the silence is so difficult to ignore, the numbers must be handled carefully. Not exaggerated, not softened, not poetic. When treated conservatively, they still lead to the same uncomfortable conclusion. Something does not add up. The Milky Way is approximately 100,000 light-years across. That sounds vast until it is placed alongside time. Light itself, the fastest thing in the universe, takes 100,000 years to cross it. But civilization does not need to travel at the speed of light to leave evidence. It only needs time. And time is abundant. Star formation in the Milky Way has been ongoing for more than 13 billion years. Our Sun is not among the first generation of stars, nor even the second. It is a later product of a galaxy that had already enriched itself with heavy elements through countless supernova explosions. Those heavy elements are critical. Carbon, oxygen, nitrogen, iron, and phosphorus are not primordial. They are forged inside stars and spread through stellar death. This means that the earliest epochs of the galaxy were less hospitable to life, but not indefinitely so. After a few billion years, the chemical ingredients necessary for rocky planets and complex chemistry became widespread. By the time the galaxy was roughly 3 billion years old, it was already capable of producing planetary systems similar to our own. That leaves a window of more than 10 billion years during which life could have emerged elsewhere. 10 billion years is an extraordinary amount of time. On Earth, the transition from single-celled organisms to intelligent beings capable of spaceflight occurred in less than 4 billion years. Even allowing for enormous variation, the available timescale elsewhere remains vast. Modern astronomical surveys indicate that planets are not rare outcomes. On average, each star hosts at least one planet. Many host several. A substantial fraction of stars host rocky planets roughly Earth-sized. A smaller but still significant fraction host such planets within their habitable zones. Even conservative estimates suggest that 1 in 5 Sun-like stars may host an Earth-sized planet in a region where liquid water could exist. When multiplied across tens of billions of stars, the result is not speculative. It is staggering. At this point, the argument does not require optimism about life. It does not require assuming that life appears easily. Even if life arises on only 1 in 1,000 habitable planets, the Milky Way would still host millions of living worlds. If intelligence arises on only 1 in 1,000 of those, thousands of technological civilizations would still be expected over the galaxy's lifetime. These are deliberately pessimistic assumptions. Yet even under them, silence remains difficult to justify. Time compounds the problem. A civilization does not need to be common to matter. It only needs to arise once and survive long enough. Once a technological species gains the ability to alter its environment, to leave artifacts, to modify planetary atmospheres, or to exploit stellar energy, its presence becomes visible across interstellar distances. Even a single civilization that achieved this stage millions of years ago would have had ample opportunity to reshape portions of the galaxy in detectable ways. Interstellar expansion does not require reckless ambition or rapid colonization. Even cautious exploration would suffice. If a civilization launched probes to nearby stars every few thousand years, and each probe established new outposts capable of launching further probes, expansion would proceed as a slow but unstoppable wave. At this pace, the entire galaxy could be traversed in a few million years. Compared to the galaxy's age, this is effectively instantaneous. The key point is not whether such expansion would occur, but that it could. Physics does not forbid it. Energy constraints do not forbid it. Engineering challenges do not forbid it. The only constraints are motivation, survival, and choice. Yet even if most civilizations chose not to expand, it would only take one exception to leave a permanent signature. This is where the paradox sharpens. The absence of evidence is not merely a lack of contact. It is a lack of indirect signs. No obvious megastructures. No galaxy-spanning energy usage. No artificial rearrangement of stellar systems. No persistent communication signals. No industrial chemical fingerprints in exoplanet atmospheres that defy natural explanation. The universe appears not only unvisited, but untouched. Some have argued that humanity may simply be early, that intelligent life has not yet had time to spread. But this explanation struggles against the age of the galaxy. Being early would require that intelligent life arises almost exclusively in the last fraction of cosmic history, clustered within a narrow temporal window. There is no known physical mechanism that would enforce such synchronization across billions of star systems. Others suggest that technological civilizations may be extremely short-lived. That intelligence emerges frequently but destroys itself before achieving lasting impact. This possibility cannot be dismissed, but it raises its own questions. If self-destruction is common, then intelligence may be inherently unstable. If instability is built into the nature of technological progress, then silence becomes a warning rather than a mystery. Another possibility is that advanced civilizations do not produce easily detectable signatures, that their technologies are efficient, subtle, or fundamentally different from anything humanity anticipates. This too remains plausible. Human expectations are shaped by human history, which may be a poor guide to alien behavior. But even highly efficient systems must obey thermodynamics. Energy use produces waste heat. Large-scale computation produces detectable effects. Complete invisibility is difficult to maintain indefinitely. The paradox, therefore, does not resolve itself easily. Each attempted solution shifts the problem rather than eliminating it. The numbers remain. The time remains. The silence remains. Importantly, the paradox does not imply danger, salvation, or destiny. It implies ignorance. It reveals the limits of current understanding. Humanity knows enough to ask the question, but not enough to answer it. The universe has provided sufficient data to make the absence of others meaningful, but not enough to explain it. This places the Fermi Paradox in a unique category among scientific problems. It is not a single, unknown variable. It is a conflict between multiple well-supported observations. The size of the universe, the age of the galaxy, the prevalence of planets, the speed of technological change, the lack of visible intelligence. All of these are independently supported. Taken together, they form a contradiction that demands resolution. The next step is not to imagine visitors or messages, but to examine barriers. If something prevents life from becoming widespread, it must act repeatedly and reliably across the galaxy. This idea leads to one of the most influential and unsettling frameworks proposed to explain the silence, the concept known as the Great Filter. The Great Filter is not a single event, nor a specific catastrophe. It is a concept, a way of describing whatever prevents life from becoming visible on a galactic scale. If intelligent civilizations are rare, short-lived, or systematically eliminated, then some barrier must exist somewhere along the path from lifeless matter into stellar presence. That barrier is the filter. The path itself is long and complex. It begins with a lifeless planet composed of simple elements. From there, chemistry must organize itself into self-replicating systems. Those systems must survive environmental instability. Simple life must become complex. Complex life must develop intelligence. Intelligence must produce technology. Technology must persist without destroying its creators. At each step, failure is possible. The Great Filter may lie at any one of these stages. One possibility is that the filter lies behind us. In this scenario, one or more steps already passed by life on Earth are extraordinarily unlikely. The origin of life itself may be the critical bottleneck. Despite decades of research, no definitive explanation exists for how non-living chemistry transitioned into self-replicating biological systems. Laboratory experiments can create organic molecules, even complex ones, but the leap to true life remains elusive. If this transition requires an extremely rare combination of conditions, then most habitable planets may remain sterile indefinitely. If this is true, then Earth represents an exceptional outcome, a planet that crossed a threshold that almost none ever do. The silence of the universe would then reflect absence rather than concealment. Life would be rare not because it cannot exist elsewhere, but because it almost never begins. Another possibility is that simple life is common, but complexity is rare. On Earth, single-celled organisms dominated the planet for billions of years. The emergence of complex cells with internal structures occurred only once, and it took nearly 2 billion years. This transition required a precise form of symbiosis, one cell incorporating another without destroying it, forming the energy-producing structures that power all complex life today. If this event is extraordinarily unlikely, then most living worlds may remain locked in a microbial state forever. Even beyond that, the leap to multicellular organisms presents another potential barrier. Multicellular life requires cooperation between cells, specialization, and systems that suppress individual reproduction for the benefit of the whole. These are not trivial evolutionary innovations. They represent a shift from competition to coordination. If this transition is rare, then complex ecosystems may be uncommon even on living planets. Intelligence introduces yet another filter. Despite the vast diversity of life on Earth, only one species developed abstract reasoning, cumulative culture, and advanced tool use. Many animals exhibit problem-solving abilities and social complexity, but none crossed the threshold into technological civilization. Intelligence may not be a natural endpoint of evolution, but an unusual side branch that requires very specific pressures and environments. If any of these early filters are sufficiently strong, then humanity may already be past the most difficult barriers. The universe would appear empty, not because life fails later, but because it almost never reaches complexity at all. This interpretation is unsettling, but in a quiet way. It implies rarity rather than danger. The more disturbing possibility is that the filter lies ahead. If early steps are relatively easy, if life and intelligence emerge frequently, then something must prevent civilizations from surviving long enough to leave lasting marks on the galaxy. In this case, the silence becomes a warning rather than a coincidence. It suggests that advanced technological societies tend to collapse, self-destruct, or otherwise disappear before spreading far. Several mechanisms could produce such an outcome. One is environmental collapse. A species capable of altering its planet's climate and ecosystems may do so faster than it can adapt. Industrial activity, resource depletion, and ecological instability could undermine the foundations of civilization. If this pattern repeats universally, then technological progress may carry an inherent risk of planetary failure. Another possibility is technological self-destruction. Advanced energy sources, weapons, or autonomous systems may outpace the social and ethical frameworks required to manage them safely. A civilization may reach a point where it possesses the power to end itself, long before it possesses the wisdom to avoid doing so. Nuclear war, runaway artificial intelligence, or unforeseen consequences of powerful technologies could eliminate civilizations shortly after they become detectable. There is also the possibility of stagnation rather than catastrophe. The civilization may survive, but lose the drive to expand or communicate. Cultural collapse, extreme risk aversion, or inward-focused development could lead to technological plateau. In such cases, intelligence persists but leaves little outward trace. The galaxy would still appear silent. Some interpretations suggest that survival beyond a certain technological threshold requires deliberate restraint. Civilizations that broadcast their presence or build large-scale structures may attract risks they cannot manage. In this view, silence is not failure, but strategy. The civilizations that survive are the ones that remain undetectable. The Great Filter does not specify which of these explanations is correct. It simply reframes the paradox. Instead of asking why the universe is empty, it asks where the failure occurs. Before intelligence, or after it. Before technology, or after it. Before expansion, or during it. The emotional implications of this framework are unavoidable, but the concept itself is not emotional. It is analytical. It arises naturally from combining probability with observation. If the galaxy should be full of life but is not, then something must consistently intervene. If the filter lies behind us, then humanity is extraordinarily rare. If it lies ahead, then humanity is precarious. Both possibilities carry weight. Neither is comforting. What makes the Great Filter particularly powerful is that it does not rely on speculation about alien motives. It does not assume hostile visitors or benevolent guardians. It assumes only that certain outcomes are difficult to achieve repeatedly. It explains silence without invoking intention. Yet even the Great Filter may not be singular. There may be multiple filters, each eliminating a fraction of potential civilizations. The cumulative effect could be devastating. Even if each barrier removes only most, rather than all, the end result would still be an almost empty galaxy. At this stage, the paradox becomes less about aliens and more about survival. It becomes a mirror, a way of asking whether intelligence is inherently fragile, whether technological power is sustainable, and whether long-term stability is achievable at all. The next set of explanations shifts the focus away from failure and toward choice. Perhaps civilizations survive, but do not behave as expected. Perhaps silence is not the result of collapse, but of deliberate quiet. Not all explanations for the silence require collapse or extinction. Some require only restraint. One of the simplest assumptions built into early expectations of extraterrestrial intelligence was that advanced civilizations would want to announce themselves, that they would broadcast signals, construct vast structures, or otherwise make their presence obvious. This assumption may be flawed. Human history offers a limited reference frame. Technological development on Earth has been noisy, inefficient, and highly visible. Early radio transmissions leaked into space unintentionally. Industrial activity altered atmospheric chemistry. Large-scale energy use produced heat and pollution. These signatures make humanity temporarily detectable. But there is no guarantee that this phase is permanent, nor that it represents an optimal trajectory. Advanced civilizations may learn to minimize their detectability. Energy efficiency improves with technological maturity. Waste heat can be reduced. Communication can shift away from omnidirectional broadcasting toward tightly targeted or entirely internal systems. As technology advances, the need to radiate energy indiscriminately decreases rather than increases. A highly developed civilization may be quieter than a developing one. From this perspective, radio silence is not surprising. Radio communication may represent a brief window in technological history. A civilization broadcasts unintentionally for a short period, then transitions to more efficient, less detectable methods. If this window lasts only a few centuries, the probability of overlapping with another civilization at the same stage becomes extremely low, even in a galaxy filled with intelligence. Detection strategies may also be misaligned. Human searches have focused heavily on narrowband radio signals and optical beacons, methods that assume deliberate outreach. But an advanced civilization may have no incentive to communicate openly across interstellar distances. Communication latency alone introduces delays of decades or centuries. Dialogue becomes impractical. Information exchange becomes asynchronous. Over time, the motivation to maintain such contact may diminish. There is also the issue of security. Broadcasting one's location across the galaxy may carry risks. Even if hostile civilizations are rare, the consequences of attracting attention from a single predatory or unstable intelligence could be catastrophic. In an environment where the distribution of intentions is unknown, silence becomes a rational strategy. This line of reasoning leads to what is sometimes called the dark forest interpretation. In this view, the universe is not empty, but cautious. Every civilization exists in a state of mutual uncertainty. Revealing one's presence risks destruction. Remaining silent increases the probability of long-term survival. Under such conditions, the safest strategy is concealment. This interpretation does not require hostility to be common. It requires only that hostility exists at all. When stakes are existential, even low-probability threats influence behavior. Silence becomes the default. Technological invisibility may also arise unintentionally. Civilizations may transition away from physical expansion altogether. Digital environments, simulated realities, or inward-focused development could offer richer experiences than interstellar colonization. If intelligence shifts its priorities from physical presence to internal complexity, its footprint may shrink rather than grow. In such scenarios, civilizations still exist, still think, still create, but they do so without altering stars or reshaping galaxies. Their energy use remains local. Their structures remain compact. Their presence blends into natural background processes. The universe appears untouched, not because it is uninhabited, but because intelligence has learned to coexist quietly within it. Another possibility is that intelligence migrates away from detectable environments. Advanced civilizations may relocate to regions of space that are difficult to observe, such as the outskirts of galaxies or low radiation voids. They may exploit physical regimes humans rarely study. Their activities may occur at energy scales or wavelengths not routinely monitored. Some speculative models suggest that intelligence may even abandon biological substrates altogether. Post-biological entities may exist as information systems operating near the limits of physical efficiency. Such systems would generate minimal waste heat, occupy minimal space, and leave minimal detectable traces. From a distance, they would be indistinguishable from natural processes. These ideas shift the paradox away from failure and toward misinterpretation. Perhaps the galaxy is not silent. Perhaps it is simply quiet in ways humans do not yet recognize. Another family of explanations suggests that advanced civilizations do not expand uniformly. Instead of spreading across the galaxy, they may remain confined to their origin systems or small clusters of stars. Expansion may be unnecessary, undesirable, or counterproductive. Local optimization may outperform cosmic ambition. This contradicts early assumptions that intelligence naturally seeks growth. Growth is a biological imperative under scarcity. Under abundance, priorities change. A civilization capable of controlling its energy resources, managing its environment, and sustaining itself indefinitely may have little incentive to expand outward. Expansion introduces risk, complexity, and conflict. Stability may be preferable. Under this model, the galaxy could host many isolated civilizations, each content within its own system, each leaving minimal detectable traces beyond its immediate vicinity. Detection becomes unlikely unless one happens to be very close. The silence may also reflect scale mismatch. Human observational windows are narrow in both time and space. Civilizations may operate on timescales far longer than those humans consider meaningful. Activities may unfold over tens of thousands or millions of years. From a human perspective, such changes would appear static. If a civilization engages in projects that span geological timescales, such as stellar engineering or long-term energy harvesting, its actions may not register as artificial within short observation periods. Detection requires patience far beyond current technological practice. Some models propose that intelligence becomes more subtle as it advances, not more dramatic. Early technological phases are messy and visible. Mature phases are quiet and efficient. Humanity may currently occupy a brief, detectable stage that most civilizations pass through quickly. The silence may therefore reflect maturity rather than absence. This interpretation carries an implicit warning. If detectability correlates with vulnerability, then remaining visible may be dangerous. Civilizations that survive long enough to become ancient may do so precisely because they stop advertising their existence. At this point, the paradox has shifted again. The absence of evidence no longer implies absence of life. It implies limitations in expectation. Humanity may be searching for signs that advanced intelligence no longer produces. Yet even this does not fully resolve the problem. Total invisibility is difficult to maintain forever. Thermodynamics still applies. Information processing still consumes energy. Waste heat must go somewhere. At sufficiently large scales, even efficient systems produce detectable anomalies. This brings the discussion to a deeper question. If advanced civilizations exist and remain undetected, are they small, restrained, and local, or are they operating in ways fundamentally beyond current understanding? The answer matters, because it determines whether the silence reflects safety, indifference, or something else entirely. Another explanation removes intention from the equation altogether. Perhaps advanced intelligence does expand, but does so slowly, deliberately, and selectively. Instead of saturating the galaxy, civilizations may explore, study, and withdraw. Presence becomes transient rather than permanent. In this scenario, the galaxy experiences waves of exploration followed by long periods of quiet. A civilization may pass through a region millions of years before humans arise, leaving little trace behind. Geological processes erase evidence. Orbits change. Stars evolve. The record disappears. Under this model, the galaxy is not static. It is dynamic on timescales that exceed human observation. Civilizations may come and go. The present moment may simply fall between eras of detectable activity. This explanation does not contradict the numbers. It reframes them. Time remains abundant, but visibility becomes episodic. Detection becomes a matter of coincidence rather than inevitability. By this stage, the paradox has accumulated layers: rare life, fragile intelligence, silent survival, invisible technology, temporal mismatch. None are mutually exclusive. The true explanation may involve several acting together. The next set of ideas moves beyond silence and into deliberate non-interference. If advanced civilizations exist and are aware of younger ones, they may choose to remain hidden for ethical reasons rather than strategic ones. The idea of deliberate non-interference arises naturally once the possibility of advanced, long-lived civilizations is taken seriously. If intelligence can persist for millions of years, then it will inevitably encounter younger civilizations at earlier stages of development. At that point, a choice emerges. Intervene, observe, or avoid. One proposal that addresses the silence without invoking collapse or invisibility is commonly referred to as the zoo hypothesis. In this framework, advanced civilizations are aware of emerging intelligences but intentionally avoid contact. Younger worlds are allowed to develop independently, free from external influence. Observation replaces interaction. Silence becomes policy rather than absence. This idea is often dismissed as speculative, but it rests on assumptions that are neither mystical nor implausible. Human societies already practice forms of non-interference. Wildlife preserves exist to protect ecosystems from destruction. Uncontacted human populations are deliberately left alone, not because contact is impossible, but because it causes harm. Ethical restraint emerges when power asymmetry becomes extreme. On a galactic scale, that asymmetry would be vast. A civilization millions of years older than humanity would possess technologies and knowledge so advanced that contact could irreversibly alter a developing species. Even well-intentioned interaction could destabilize culture, belief systems, and long-term development. Silence may be viewed as the least harmful option. Under this model, the galaxy may be inhabited but carefully managed. Regions containing emerging civilizations could be designated as protected zones. Observation would occur covertly, using technologies designed to avoid detection. The absence of obvious artifacts becomes intentional rather than accidental. This explanation also accounts for the lack of partial evidence. If non-interference is enforced consistently, then detectable megastructures, probes, or signals would be avoided near developing worlds. Activity would be displaced or concealed. From the perspective of a young civilization, the universe would appear empty, even if it is not. Critically, this hypothesis does not require coordination across the entire galaxy. It requires only that the oldest, most influential civilizations adopt similar ethical norms. Once established, such norms could persist through cultural transmission, treaties, or shared understanding of long-term risk. Younger civilizations that violate non-interference may be discouraged or prevented from doing so. The zoo hypothesis is unfalsifiable with current technology. Any absence of evidence can be interpreted as successful concealment. This makes it scientifically weak as a predictive model, but logically consistent as an explanation for silence. It cannot be disproven, but it cannot be confirmed either. Its value lies not in its truth, but in what it implies. If non-interference is common, then detectability may correlate with immaturity. Young civilizations are visible because they have not yet learned restraint. Older ones are quiet because they have. Another variant of this idea suggests that contact is conditional rather than forbidden. Civilizations may be observed until they reach certain thresholds. These thresholds could be technological, social, or ethical. Mastery of energy without planetary destruction. Stable, global cooperation. Long-term planning beyond immediate survival. Only once these criteria are met would contact occur. Under such a system, silence becomes temporary rather than permanent. Contact is delayed, not denied. The universe remains quiet, not because it is empty, but because most civilizations are still developing. This interpretation reframes the paradox as a timing issue. Humanity may simply not yet qualify. The absence of contact says nothing about the existence of others, only about readiness. There is also the possibility that observation itself is passive. Advanced civilizations may not actively monitor younger ones. Instead, they may maintain a general policy of non-engagement. Detection is avoided not to protect the observed, but to avoid risk to the observer. Younger civilizations are unpredictable. Their behavior is unstable. Engagement introduces uncertainty. In this view, silence is neutral. Younger civilizations broadcast without understanding the risks. Older ones remain silent because they understand them too well. The zoo hypothesis becomes more unsettling when combined with the great filter. If advanced civilizations observe younger ones, they may also observe failure. They may have watched countless worlds collapse, self-destruct, or stagnate. Silence could be informed by experience rather than theory. If this is the case, then the absence of contact is not indifference. It is caution shaped by history. However, this explanation raises uncomfortable questions. If advanced civilizations exist and observe failure without intervention, then survival is not guaranteed. Observation does not imply protection. Non-interference may allow extinction as readily as growth. The universe would not be hostile, but it would not be benevolent either. At this point, the paradox intersects with ethics rather than physics. The silence could reflect restraint, fear, wisdom, or indifference. Each interpretation carries different implications, but all remain consistent with the same observation. Nothing is heard. Yet even deliberate concealment has limits. Total invisibility across the entire galaxy, sustained over billions of years, would require extraordinary coordination and discipline. It would require that no civilization ever deviates, ever expands recklessly, ever leaves an accidental trace. This seems unlikely, which brings the discussion back to rarity. Perhaps there are not many civilizations capable of enforcing such policies. Perhaps there are very few that survive long enough to do so. Perhaps there is only one. The Rare Earth framework approaches the paradox from a different angle. Instead of focusing on intelligence or behavior, it focuses on environment. It asks whether planets capable of sustaining complex life for billions of years are far rarer than current discovery methods suggest. Habitability, in this view, is not a single condition, but a fragile balance of many. Liquid water alone is insufficient. A planet must maintain surface stability across geological timescales. This requires a star that burns steadily, without extreme variability. Many stars flare violently, emitting bursts of radiation that can strip planetary atmospheres or sterilize surfaces. Others evolve too quickly, leaving insufficient time for complex life to develop. Sun-like stars may be less common than assumed. Planetary mass also matters. A world too small loses its atmosphere. A world too large retains thick hydrogen envelopes that prevent Earth-like conditions. Orbital dynamics introduce further constraints. Highly elliptical orbits produce extreme temperature swings. Tidal locking may eliminate climate stability. The presence of large gas giants can either protect inner worlds by deflecting impacts or destabilize them through gravitational disturbance. Earth benefits from a large moon. The moon stabilizes axial tilt, moderating seasonal extremes. Without it, chaotic tilt variations could produce severe climate shifts incompatible with long-term biological stability. Large moons may be rare outcomes of planetary formation. Earth's moon appears to have formed through an unusual high-energy collision early in the planet's history. Plate tectonics introduce another constraint. Tectonic activity recycles carbon and regulates atmospheric composition through long-term feedback mechanisms. Without it, planets risk runaway greenhouse states or permanent ice ages. The conditions required for sustained tectonics depend on internal heat, composition, and water content. Many planets may lack this balance. Magnetic fields further complicate habitability. A strong magnetic field shields a planet from stellar radiation and solar wind, preventing atmospheric erosion. Mars likely lost much of its atmosphere after its magnetic field weakened. Sustained magnetospheres may be uncommon. Even with all these factors satisfied, stability is not guaranteed. Earth has experienced multiple mass extinctions. Asteroid impacts, volcanic events, and climate shifts repeatedly reset evolutionary progress. Complex life survived, but narrowly. A slightly different sequence of events could have ended the experiment permanently. From this perspective, intelligence is not merely rare. It is contingent. It emerges only when a planet avoids catastrophic disruption long enough for evolution to explore complexity. Many worlds may host life briefly, only to lose it. Others may host simple organisms that never escape microbial dominance. This framework does not deny life elsewhere. It restricts it, It suggests that while the galaxy may host many living worlds, very few sustain the uninterrupted stability required for advanced intelligence. The silence becomes a statistical outcome rather than a mystery. However, even rare Earth models face difficulty explaining total silence. Rare does not mean singular. Across hundreds of billions of stars and billions of years, even improbable sequences should occur more than once. If advanced civilizations are possible at all, the galaxy still offers vast opportunity. This leads to a hybrid view. Perhaps complex life is rare, intelligence rarer still, and technological longevity rarer again. Each stage reduces the number dramatically. By the time a civilization capable of lasting millions of years arises, the expected count may drop below 1 per galaxy. Under such conditions, silence becomes expected, not because intelligence cannot arise, but because it almost never persists. This interpretation shifts the paradox away from aliens and toward time. A civilization may arise, develop technology, and disappear within a few thousand years. From a cosmic perspective, it flickers briefly and vanishes. Detecting such flickers across interstellar distances becomes extraordinarily unlikely. Humanity itself may occupy such a flicker. Radio leakage, industrial signatures, and early space activity represent a narrow window. If this window closes before interstellar expansion occurs, humanity would leave little trace beyond its immediate neighborhood. After a few million years, even planetary signatures could fade. In this light, the silence may reflect not emptiness, but brevity. Civilizations may rise and fall like sparks in a dark forest, each too brief and too distant to notice the others. At this stage, the paradox no longer feels paradoxical. It feels statistical. The universe may be full of failed experiments, not because failure is inevitable, but because success requires extraordinary alignment across time, space, and circumstance. The remaining question then becomes observational. If intelligence is rare and fleeting, how should it be searched for? What signatures would persist long enough to be detected? And what assumptions must be abandoned? This brings the discussion back to human observation itself. The silence may say less about the universe and more about the limitations of current methods. The search for extraterrestrial intelligence has never been a passive exercise. It has been shaped by assumptions, constraints, and practical limitations from the beginning. Understanding the silence requires understanding what has actually been searched for, how long it has been searched for, and what kinds of signals current methods are capable of detecting. Most searches have focused on electromagnetic communication, particularly radio waves. This choice was logical. Radio waves travel long distances, pass through interstellar dust, and require relatively modest energy to produce. Early human technology naturally leaked radio emissions into space, making radio appear to be a universal signature of emerging technological civilization. But radio detectability is narrow in both time and direction. Signals weaken rapidly with distance unless deliberately focused. A civilization must broadcast continuously, in the right frequency range and in the right direction for another civilization to detect it. Even powerful transmissions become indistinguishable from background noise over interstellar distances, if not aimed precisely. This creates a fundamental detection bias. The absence of detected radio signals does not imply the absence of intelligence. It implies the absence of continuous, intentional broadcasting aligned with human listening strategies during a brief observational window. Optical searches introduce similar limitations. Laser pulses can carry vast amounts of information, but they require precise targeting and timing. Detection depends on the alignment of transmitter and receiver at the exact moment of transmission. Miss the moment, and the signal is gone. Beyond communication, astronomers have searched for indirect signs of technology. Excess infrared radiation could indicate waste heat from large-scale energy use. Unusual stellar dimming patterns could suggest artificial structures. Atmospheric spectroscopy might reveal industrial chemicals inconsistent with natural processes. So far, none of these searches have produced unambiguous results. But each method surveys only a fraction of the galaxy over a fraction of time, with limited sensitivity. The Milky Way contains hundreds of billions of stars. Only a tiny subset have been examined in detail. Even fewer have been monitored continuously. The silence, therefore, is not absolute. It is statistical. Humanity has sampled an extraordinarily small portion of a vast parameter space and found nothing conclusive. This is meaningful, but not decisive. Detection is further complicated by anthropocentric assumptions. Human technology follows human priorities. It assumes energy-intensive infrastructure, electromagnetic communication, and visible expansion. Alien intelligence may not follow these patterns. Different evolutionary paths, environments, and cognitive architectures could produce technologies that do not resemble anything humans anticipate. Civilizations may use communication methods beyond electromagnetic radiation. Gravitational waves, neutrino beams, or quantum-scale phenomena could carry information in ways not yet practical for human detection. Even within known physics, advanced encoding schemes could mask signals within natural noise. There is also the issue of scale. Human detection thresholds are tuned to planetary or stellar phenomena. Activities smaller than these scales vanish into background processes. Activities larger may blend into natural astrophysical variation. Distinguishing intent from nature becomes increasingly difficult as systems grow more complex or more efficient. Time remains the most severe limitation. Human technological civilization has existed for only a few centuries. Radio astronomy has existed for less than one. Continuous monitoring of large regions of space spans decades at most. Against a backdrop of billions of years, this represents an almost negligible sample. A civilization that broadcasts for 1,000 years would be nearly invisible unless another civilization happened to listen at exactly the right moment. Overlapping detection windows may be rare even if intelligence is common. This temporal mismatch explains why the silence is not surprising on short timescales. But it does not eliminate the paradox entirely. Over billions of years, some signals should persist. Some artifacts should remain. Some signatures should be detectable. The absence of such persistent evidence suggests one of two things. Either advanced intelligence rarely produces long-lasting signatures, or such intelligence is genuinely rare. SETI, therefore, does not test whether intelligence exists everywhere. It tests whether intelligence behaves in detectable ways over long periods. The failure to detect signals does not falsify the existence of alien civilizations. It constrains their properties. The silence implies that if advanced civilizations exist, they are either short-lived, quiet, localized, or technologically subtle. Or some combination of all four. This reframing matters. It shifts the paradox away from expectation and toward inference. Instead of asking why aliens have not contacted humanity, the better question becomes why intelligence does not leave obvious traces. At this stage, the paradox no longer points outward. It points inward. It forces reconsideration of human assumptions about progress, expansion, and technological destiny. Perhaps the expectation that intelligence naturally spreads, signals, and reshapes its environment is flawed. If so, the silence is not evidence of failure. It is evidence of restraint, impermanence, or alternative trajectories. The final question then becomes existential rather than observational. If intelligence rarely persists, or rarely expands, or rarely signals, what does that imply for humanity's future? When all proposed explanations are set side by side, a pattern emerges. No single solution fully resolves the Fermi Paradox. Each addresses part of the silence, but none removes it entirely. This is not a failure of theory, but a reflection of complexity. The universe does not owe simple answers. Life may be rare. Intelligence may be fragile. Technology may be brief. Civilizations may choose silence. Observation may be limited. Time may erase evidence. Each of these forces alone could reduce detectability. Acting together, they may reduce it to near zero. The paradox, then, is not proof of absence. It is proof of constraint. Whatever intelligence is, wherever it appears, it does not reliably reshape galaxies, announce itself, or persist indefinitely. The universe is not crowded with visible minds. That fact remains regardless of which explanation is favored. This silence does not imply meaning, purpose, or intent. It implies uncertainty. It reveals that intelligence is not a guaranteed outcome of evolution, nor a stable end state. It may be a transient phase, a narrow window between biological emergence and eventual disappearance. From a scientific perspective, the paradox remains open. No hypothesis has been confirmed. No mechanism has been ruled out. The question persists not because it is mystical, but because available evidence is incomplete. The universe has provided enough data to make the problem real, but not enough to resolve it. In that sense, the Fermi Paradox is not a mystery waiting for discovery. It is a boundary, a reminder of how little is known about long-term survival under physical law, a reminder that intelligence may be constrained by forces not yet understood. The stars continue to burn. Planets continue to orbit. The galaxy continues its slow rotation. And within that vast structure, silence remains the dominant signal. Whether that silence reflects rarity, fragility, restraint, or simple chance is still unknown. What is known is that the question itself arises naturally from observation, not imagination. Where are all the aliens remains unanswered, not because it is unscientific, but because it is one of the few questions that exposes the limits of current knowledge. And until those limits change, the universe remains quiet.